It's a very nice website in Colorado. The PHET, they have a lot of simulations that would help you visualize these concepts from physics. So let me pull that up for you. This thing right here. So you can just Google PHET, University of Colorado. You'll get to this page right here, this quantum mechanical tunneling applet. And so you just click on Run Now when you get to that page, and then you run the program. Running. All right, so when you get to this side, the first thing you want to do is click on plane wave, because we're only going to be interested in stationary states. All right, we'll talk about wave packets sometime later. So click on plane wave, and let's just examine what happens when there is no barrier. So here's your potential energy up here. Okay, so it's V naught from x equals 0 to x equals L. So looks like our L here is what? 1 nanometer, right? From 0 to 1 nanometer, you have a barrier. So you can change that, the width of that barrier, by just dragging this, okay? And you can change your energy. This is your energy. You can make it less than V naught. You can make it greater than V naught. Okay, so that's greater than V naught there. That's less than V naught. So you can change the energy of your particle. You can also change the height of your barrier. So let's just keep it like that for now. All right, and what you're seeing right now, the red curve, you'll notice, is the real part of your wave function. What's your wave function? Remember, it's equal to psi equals what? Let's just make this to make things easier to understand for now. Let's just make this a free particle. Okay, so stationary state, all right, is psi equals what? This particle is moving to the right. So what's my momentum here? Positive h bar k, right? So that means psi must be equal to e to the I k x, positive. Okay. You can see the wave back, your wave is moving to the right. Why are we calling it stationary state when it's moving? Look at the magnitude. It's constant. Down here, a plot of the probability density, it's constant. Okay, stationary state, the probability density doesn't change. All right. Why is the function itself moving? Well, you have to be looking at the both real and imaginary part. So there's the imaginary part right there. Okay. And what do these functions look like? Sine and cosine functions, right? E to the I k x is nothing more than what? Cosine, Euler formula. This is cosine kx plus I sine kx. So you have a cosine function. The real part is cosine kx. The imaginary part is sine kx. So the blue curve is sine kx, and then the red curve is cosine kx. All right. So if you add those two together and multiply sine kx by I, you get your actual psi. You cannot plot the imaginary, the complex function itself. So you have to plot the real part and the imaginary part separately. If you take the absolute value, you'll find, what's the absolute value of this? It's going to be cosine squared plus sine squared. Trigonometric identity, cosine squared theta plus sine squared theta is equal to 1. So you can see the probability density is constant, is equal to 1. Okay, it's 1 right there. All right, what happens if we were to change your energy? What happens now? Look what happened. Oops, sorry. If I'm going to drag this, what's happening? The wavelength changes, right? Why is that wavelength changing? Because your wavelength depends on k. If you recall, that's just equal to what? 2 pi over lambda, right? A good way to write your sine and cosine functions so you can immediately identify the wavelength is to write it like this: sine 2 pi x over lambda. So you can identify 2 pi over lambda here as k. or whether you're doing it sine or cosine. Right, so what happens when you increase the energy? What was the energy of a free particle? It's p squared over 2m, right? So h bar squared, k squared over 2m. The higher the k, the higher the energy, the higher the momentum. What happens? What happens to the wavelengths? The higher the k, what happens to your wavelength? K is equal to 2 pi over lambda. Oh, sorry. The larger the k, the shorter the wavelength, right? And in fact, you can show that. Let me rewrite this. Let me write this as lambda equals, what's lambda equal to in terms of k? 2 pi over k, right? And what is k? It's just p over h bar, right? And what is p over h? So if I have h bar in the denominator of my denominator, that becomes what? 2 pi h bar over p, right? And what is h bar? H over 2 pi. So this is going to be 2 pi times h over 2 pi divided by p. Your 2 pi cancels out. So your lambda is equal to h over your lambda is nothing more than h over p. What did we call that lambda before? De Broglie wavelength. So the wavelength of your wave function here is really the de Broglie wavelength of your particle. Okay? So let me clear that. So why is this thing moving? Because what you're plotting here is not the little psi, it's the big psi. What's big psi? The time-dependent the overall wave function. That's the solution to your time-dependent Schrodinger equation. Big psi is equal to little psi times what? Since this is a stationary state, e to the negative I e t over h bar. Okay? And your psi right here is your e to the I kx. So this is what you're plotting here is e to the I kx times e to the negative I e t over h bar. Okay? And this is basically the same type of function that you saw when we did the animation for the electromagnetic wave. Okay, you're going to have a sinusoidal function that depends on x and t. Right? So you can express this in terms of sines and cosines, and you can see it's basically the same equation that we use to animate your electromagnetic radiation. Okay, electromagnetic wave. So that is your wave function right there. So what happens now if we were to, okay, like I said, if you want it moving to the left, that's what the wave looks like. Now down here you can pause it, so you can take a snapshot of the wave function at any given time. All right, so this is, you can, this down here, this button right here just sets it back to time 0. And this is the assumption in this calculation, in the calculation that was used to do this simulation, this is the assumption of what psi is at time 0. Okay, and so As time advances, your psi will change according to the time-dependent Schrodinger equation. So that's what's going to happen to your psi. All right. So that's for a free particle. What happens if you put a barrier?